Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on June 28, 2025, so about 3 days ago. This paper introduces a listener-based training method that boosts a model's performance on new, out-of-distribution data by up to 6%. The paper is titled, Listener-Rewarded Thinking in Vision Language Models for Image Preferences, and the implications for aligning models with human intent are pretty significant. The authors tackle the key challenge of teaching models not just to be correct, but to explain their reasoning in a persuasive way. On Hugging Face, you can find the 8 billion parameter model, complete with code examples showing how it reasons about and chooses between two different images. So, to illustrate this core problem, this first figure really gets to the heart of it. We see two images, a tiger and a horned lion, with the prompt hyperrealism animal kingdom. Now, a model trained with a standard method called Group Relative Policy Optimization, which is a technique that helps models learn to make better choices. It praises the horned lion for creativity in its reasoning. But then it contradicts itself and picks the tiger. With the new listener method added to the Group Relative Policy Optimization, the model's reasoning actually aligns with its choice. This alignment is what leads to better performance on out-of-distribution data, which is just new data the model hasn't seen before. So, to really test this new listener method, the authors needed some specific data sets. This table lays out what they used. For training, they used image reward and HPSV2, which are based on older stable diffusion models. But the real test, the key evaluation, comes from the Rapadata HSP dataset. It's a huge set, with 1.2 million votes on images from more modern models, like Dale E3 and Midjourney V6. This is their out-of-distribution dataset, meaning it's completely new to the model, which is perfect for measuring true generalization. Building on that training setup, this next figure really visualizes the core problem the authors found. On the vertical axis, we have the reasoner model's accuracy, and along the bottom is the L2 distance, which is just a mathematical way of measuring how much the main reasoner model and the frozen listener model disagree on their scores. As you can see, there's a clear trend. The more the two models disagree, so the further to the right we go, the lower the reasoner's accuracy gets. This disagreement is a powerful signal that something is wrong. So the authors use that disagreement as a reward signal, and this next chart shows the result. This is accuracy versus human preference confidence. Basically, as we go from left to right, we're looking at image pairs, where humans more strongly agreed on the best choice. And what we see is that the new reasoner plus listener model in yellow is consistently the most accurate. It clearly outperforms the standard reasoner in blue, and also a method called supervised fine-tuning, which is a common way of training models on fixed examples. And this table breaks down those accuracy numbers in more detail on the image reward test set. This is an in-domain evaluation, so the data is pretty similar to the training data. We see several methods listed, like zero-shot reasoning, which is when a model reasons about a task it's never seen before, but the real takeaway is at the bottom. The standard Group Relative Policy Optimization method hits 67.2% accuracy, and adding the listener reward pushes that to 67.4%, a new state-of-the-art on this benchmark. Okay, so that was the in-domain performance, but what about the reasoning process itself? Does it actually matter? This next table explores that exact question. It compares the standard reasoner to the listener-augmented one, both with and without access to their own thinking, or reasoning traces. For the standard reasoner, removing the thinking doesn't really change its accuracy much. But for the listener model, well, its accuracy drops from 76% all the way down to 70%. This big drop shows the listener reward is forcing the model to actually rely on its own logic. So what this all comes down to is that forcing a model to produce reasoning that convinces an independent listener, a separate vision language model that's held constant, makes the reasoning itself more robust. This paper shows a clever way to improve how we train these models to understand human preferences for images. By turning model disagreement into a dense reward signal, they not only boost accuracy, but crucially improve generalization on out-of-distribution data, which is brand new data the model has never seen before. That's all for today's AI Research Roundup. Thanks for tuning in.